Hello, everyone. The main content of our lesson today is the application of humidity sensors. First, let's delve into the development history of humidity sensors. Since the US successfully developed dip-coated humidity sensors in 1938, dozens of humidity sensors have emerged as the times require. But at present, the research of humidity sensor technology is far less accurate and perfect than that of other sensor technologies such as the temperature sensor. The reason why humidity is difficult to detect is that the transmission of humidity information is more complicated. The transmit of humidity information must be completed by the direct contact of the information material, water, to the humidity sensor, so the humidity sensor cannot be sealed and isolated and must be directly exposed to the environment to be tested. However, water is prone to three-state changes in the natural environment. When it liquefies or freezes, it often dissolves, corrodes, or ages the polymer materials and electrolyte materials of the humidity sensor, which brings disadvantages to the measurement. Therefore, there are still some problems in the long-term stability of humidity sensors. In order to obtain a long-term reliable humidity sensor, people sometimes prefer to make some changes in measurement accuracy, response time, humidity and temperature characteristics, shape and size, etc. In response to the requirements of large-scale industrial automation microcomputer control, the development direction of humidity sensors has been proposed to be miniaturization, integration, and cost reduction. Next, let's learn about methods to detect water content. Usually, the moisture content in air or other gases is called humidity, and the moisture content in solid substances is called moisture content. The percentage of the mass of water contained in a solid mass to the total mass is the value of the moisture content. The water content in solids can be detected by the following methods. First, the weighing method. The weights GH and GD of the substance before and after drying will be measured. This method is very simple, but it takes time to dry, and the real-time detection is poor, not mention some products cannot be dried. Second, the conductance method. After the solid material absorbs water, its resistance becomes small, and the water content can be detected by measuring the resistivity or conductivity. Third, capacitance method. The dielectric constant of water is much greater than that of ordinary dry solids, so the capacitance method is quite sensitive to measure the water content, and the water content of paper in paper mills can be measured by the capacitance method. Because the capacitive method involves the passage of electrical lines between the plates, the error caused by surface moisture is relatively minor. As for the measurement of capacitance value, alternating current bridge, resonant circuit, and voltammetry can be used. Fourth, infrared absorption method. Moisture absorbs infrared rays at a wavelength of 194 micrometers strongly, and the wavelength of 1.81 micrometers, which is hardly absorbed by moisture, can be used as a reference. The infrared light is switched by the filters of the two wavelengths in turn, and the water content can be detected according to the energy absorption ratio of the measured object to the two wavelengths. Fifth, microwave absorption method. Moisture absorbs microwave at a wavelength of 1.36 centimeters, but the absorption of plant fibers is several times smaller than that of water. Using this principle, the instrument can be made to measure the water content in wood, tobacco, grain, paper, and other substances. In microwave absorption method, it's crucial to consider the influence on the density and temperature of the material being tested on the detection. The equipment for this method is slightly more complex. Lastly, we will learn the applications of humidity sensors. First, the automatic dehumidification device. As shown in the figure, H is a humidity sensor, RS is a heating resistor wire, and VT1 and VT2 form a Schmidt flip-flop. The collector of transistor VT2 is loaded by relay coil K. Under normal temperature and humidity, adjust the resistance values so that VT1 is turned on and VT2 is turned off. During rainy weather, the increase in environmental humidity causes the resistance of H to drop to a certain value. At this point, the parallel resistance of RF and R2 becomes insufficient to keep VT1 conducting. VT1 cuts off, allowing VT2 to conduct. This energizes relay K, closing normally open contact 2, and energizing heating resistor RS to dissipate moisture. When the humidity decreases to a certain level, the Schmidt circuit reverses back to its initial state, VT1 conducts, VT2 cuts off, normally open contact 2 opens, RS is de-energized, heating stops, thus achieving automatic moisture control. Second, the portable hygrometer. The humidity sensor must form a corresponding circuit to measure and control the humidity. Bridge circuit is one of the main measurement circuits of resistance humidity sensor. The oscillator provides AC power to the circuit. One arm of the bridge is a humidity sensor. Due to the change of humidity, the resistance value of the humidity sensor changes, so the bridge loses balance and generates signal output. The amplifier can amplify the unbalanced signal, and the rectifier turns the AC signal into a DC signal, which is displayed by the DC milliampere meter. Both the oscillator and the amplifier are supplied with a 9-volt DC power supply. The bridge method is suitable for lithium chloride humidity sensors. The specific circuit is shown in the figure. In this lesson, we have learned the applications of humidity sensors and detection methods of water content. You can search the information after class to learn about the applications of temperature and humidity sensors in life. See you next time.